there are certain deadlock detection issues as well as their resolutions. Now, as far as the detection of the deadlock is concerned, it involves two issues. First is the maintenance of the WFG, that is wait for the graph. And the second issue is the search the WFG, that is wait for the graph, for the presence of the cycle or the knots. Now, as far as the distributed systems are concerned, uh, uh, there may be existence of the cycle at several sites. So the search for the cycle greatly depends upon how the wait for the graph of the system is represented across the system. So depending upon the manner in which the W for the graph information is maintained, as well as the search of the cycle is carried out, we have three kinds of algorithm. One is centralized, hierarchical, and distributed for the deadlock detection in the distributed system. So, but before going to explain these techniques, the correct deadlock detection algorithm must satisfy the two conditions. The first condition is the progress property. The progress property says that there are no undetected deadlocks, meaning thereby if deadlock is there, it has to be detected. So the algorithm should detect all the existing deadlock in a finite time. So once a deadlock has occurred, the deadlock detection activity should be continuously progress until the deadlock is detected. So this is the first property, that is the progress property. The second one is the safety property. No false safety property means no false deadlock to be detected. And algorithm should not report any kind of deadlock which is not existing. The deadlock which is not existing is known as phantom deadlock. In distributed system where there is no global memory and communication occurs only by the messages. So it seems to be difficult to design a correct deadlock detection algorithm because sites have to maintain the sites may obtain the out of date or the inconsistent wait for the graph of the system. So as a result, the site may detect a cycle which does not exist. So there are certain primary reasons why many deadlock detection errors reported are incorrect. And that is why these two issues are very important. Now, the deadlock detection resolution. Now, deadlock resolution involves the breaking of the existing wait for the independency, wait for dependency in the system, and wait for the graph is going to resolve the deadlock. So what it does, it involves the rolling back one or the more processes that are deadlocked and assigning their resources to the blocked processes in the deadlock so that they can resume their work, they can resume their execution. The important part of deadlock detection algorithm that it used to propagate the information regarding the wait for the dependency along the edges of the wait for the graph. So when a wait for dependency is broken, it is going to break. The corresponding information should be immediately cleaned from the system. Otherwise, it is going to, if it is not done appropriately and it is not done in time, it may result in the detection of the phantom deadlock. So let us now discuss about the algorithm. The first one is the centralized approach, a centralized algorithm for the deadlock detection. In centralized approach, there is a local coordinator at each site, which used to maintain the WFG for its local resources. And as well as there is a central coordinator um, who is responsible for constructing the union of all the individual WFG which is maintained at the different sites. Now, the central coordinator is going to construct the global weight for the graph depending upon the information which it is going to receive from the local coordinator of all the sites. So in this approach, uh, what is performed, there are two part of that. The first is if there is a cycle which is existing at the local uh, weight for the graph at any site, it represents the local deadlock. And such kind of deadlock can be detected, as well as it has to be resolved locally by the local coordinator of that particular site, if it is existing locally. Second point is the deadlock involving the resources. The deadlock involving the resources at two or more sites get reflected as a cycle in the global uh, weight for the graph. So such deadlocks are detected as well as resolved by the central coordinator. Now, it is already no need to mention, but it is important that all the local coordinator will be sending the local state information to the central coordinator in the form of a message. And we have many methods by which this message transfer took place. One is continuous transfer, in which the local coordinator sends the message providing the update is done on the local weight for the graph. And whenever an edge is added or it is deleted, it has to be informed to the central coordinator. Second one is periodic transfer. As in the case of continuous transfer, the number of messages are more. Just to reduce the number of the messages, local coordinator periodically sends the list of the edges which are added or deleted from the weight for the graph uh, since the previous message was already sent. So it is the periodic transfer. And transfer on request, in which the local coordinator sends the list of the edges which is being added or it is being deleted from the weight for the graph, since the previous message is sent only when the central coordinator makes a request to it. So in this case, transfer on request, in this particular case, the central coordinator invokes the cycle detection algorithm periodically and requests the information from each site just before invoking the algorithm. Now, this centralized approach seems to be very simple, but it suffers a lot of drawbacks. The first is the failure of the central coordinator. If the central coordinator is going to fail, everything is going to fail, because uh, we have to provide certain provision. So one such approach which can be provided for the failure of the central coordinator is to have a backup central coordinator and duplicates the job of the which used to duplicate the job of the central coordinator. Second is that the central coordinator are going to constitute the performance bottleneck. If the system is very large and there are too many sites, then the central coordinator is going to be the performance bottleneck. And third one is the that central coordinator may be able to detect the false deadlock. So because of these three reasons, the centralized approach is avoided. But even though, what is the centralized approach? So let us go with the example to uh, have the idea what is the centralized algorithm for the deadlock detection. Now let us consider here that we have three processes, P1, P2, and P3. And we have three resources, R1, R2, and R3. And these three processes, P1, P2, P3, are competing for the resources R1, R2, R3 in this following manner. The first step is the P1 is requesting for R1, and R1, since R1 is free, so R1 is allocated to it. That is being represented by the resource allocation graph. P2 is requesting for R2 and R2 is allocated to it. P3 is requesting R3 and R3 is allocated to it. And P2, again, it is going to request R1 since R1 is already allotted to P1. So it will be in the wait state. P3 is requesting R2 and R2 is already assigned to P2. So it has to wait. So this is the resource location graph after sending these 5 messages. After these 5 messages are executed, when P1 has requested, of course, the request message is not being, request age is not being given. Since R1 is allocated to it, so R1 is allocated to P1. Similarly, R2 is allocated to P2 as per its request. R3 is allocated to P3 as per its request. And P2 is going to request R1, so it will be in the wait state. So that is why it is the request edge. And P3 is requesting the resource R2. So that is why this edge is the request state. Now, suppose, meanwhile, in the step number 6, P1 is going to release R1. So whenever P1 is going to release R1, this edge will be going to be deleted. And since P2 is requiring that R1, so P2 will be allotted. So P1 is going to release R1, so R1 is allocated to now to P2. And now P1 is going to request R3, and since R3 is already allocated to P3, so it will be in the wait state. So this is the maintenance of WFG, resource allocation graph at the site S1 after the step number 7. And this is the resource allocation graph of the site S2. Because site S1 is containing resource R1 and R2, and site S2 is containing the resource R3. Now, assuming that the method of communication in between the local coordinator and the central coordinator is the continuous transfer. So if it is so, that the following sequence of the messages will be sent to the central coordinator. The first message will be from the site S1 to add an edge R1 P1 because R1 is allotted to P1. As you can see in this particular R1 to P1. So this information is going to the site. So R1 is allocated to P1. M2 is the second message in which S1, which is coming from S1 to add edge R2 P2. So R2 P2 is an edge in the central coordinator's resource allocation graph. Third message is from site S2 to add edge R3 P3. So R3 is allocated to P3, so R3 P3 is there. Now, the fourth message is from the site S1 to add edge P2 R1 because P2 is requesting for R1, so this message is included in the resource allocation graph of the central coordinator. And the fifth is from site S1 again to add an edge P3 to R2 because P3 is asking for R2, so P3 to R2. So as these 5 messages are being received by the central coordinator from the site 1 and site 2, it will be maintaining its resource allocation graph in this manner, depending upon these messages. When the 6th message is going to arrive from site S1 to delete an edge R1 P1 because P1 has released it, so this edge is being deleted. And P2 R1. P2 R1 is also being deleted because the request has been allocated. R1 has become free from P1, so R1 is allocated to P2. So it says that P2 R1 edge जो है वो delete कर दीजिए and add the edge R1 P2. The message number 7 says that from site S2 to add an edge P1 R3. So P1 R3 is being added. So as the central coordinator is receiving these messages from the different sites, after the 5, up to the step 5, up to the message 5, this central coordinator will be maintaining this. And when this 7th message is received, it will be maintaining this. This central coordinator is maintaining this. So when the central coordinator is maintaining this and this, uh, uh, there is no deadlock. But the situation may arise that if the message M7 is being received by the central coordinator before it is being received, it is going to receive the message M6. Then what will happen? Because it may be possible that during the transaction of the messages from the local coordinator to the central coordinator, it may be possible that message M6 is being delayed and M7 has come first. And whenever M7 is received before M6, then what will happen? This will going to create a cycle. So uh, if this message is being received first before the message M6, the central coordinator will be looking, and with the resource allocation graph, it will be framing the edges, and it will be getting the point that there is a cycle. A cycle is being detected. Of course, it is not the cycle, because if M6 is received first and then M7 is received first, then the central controller will be uh, drafting this resource allocation graph. But if M7 is received first and M6 is received later, then it will be saying that there is a deadlock. So this example shows that there is a possibility of detection of the phantom deadlock because M7 is received first before the M6. So since we are using a continuous transfer of the information, which is used to transfer the messages from one place to a central, local to the central. So this kind of deadlock is called the phantom deadlock. So phantom deadlock is being detected, and just because it happens due to the incomplete or the delayed information. So just to avoid this detection of phantom uh, deadlock, uh, we have a method which we have already studied earlier also. That is the why not to implement the Lamport's algorithm to append the unique global timestamp with each messages. Whenever the message is being sent, we append a unique global timestamp. Of course, M6 is generated before M7, so M7 should not be received before the M6. So in this particular example, message M7, which is from the site S2 to the central coordinator, is caused by the request from the site S1. Uh, and the message M7 will have a later timestamp than the, if we are able to provide the timestamp for all the messages. So if M6 is having lesser timestamp than M7, so M7 should not be accepted before the M6 is going to be received. So if the central coordinator receives message M7 before M6, it is going to detect a false deadlock. So before taking any action to resolve that deadlock, it has to first confirm if the detected deadlock is the real one or it is the phantom one. So for confirmation, what it used to do, it broadcast a message asking all the sites that if any site has a message with the timestamp earlier than the T for the updation of the global wait for the graph. So on receiving that particular message, if the site has a message with the timestamp earlier than the T, it will immediately send it to the central coordinator. Otherwise, it simply sends the negative reply. So after receiving all the replies from all the sites, the central coordinator updates its global wait for the graph. And if the cycle is detected before still it exists, it concludes that the deadlock is the real one, or and it starts the recovery action. So in this particular example, in reply to its broadcast message by the central coordinator, it is going to receive the message M6 from the site S1 and a negative reply from the site S2. So therefore, what it has to do after final updation of the global graph, the central coordinator's view of the system will change, and the figure this will be coming into action instead of this. So, so in this particular case, there will be no deadlock. Of course, this is going to create a deadlock, and depending upon that deadlock, it is going to take an action. But once it is exchanging, it is broadcasting a message. Once it finds that deadlock has been created, it will ask all the sites that whether the messages which it has sent, is there any message which is pending to all the sites. If the timestamp is less, M6 will inform, and M7 will say nothing. So M6 will inform, and the central coordinator, instead of framing this resource allocation graph, it is going to frame this resource allocation graph. So that is about the centralized approach. This is the total figure which is being made. This is the site S1 is going to maintain after the step number 5. This is site S2 is going to maintain after step number 5. This is the central coordinator, which is going to, because it is continuously receiving the message from the site S1 and S2. After step number 6 and 7, site S1 and S2 is being maintained, as well as the central coordinator is being maintained. But this situation may arise if the message number 7 is coming first before the message number 6. Now, the another centralized deadlock detection algorithm is the Ho-Ramamurthy algorithm. Ho and Ramamurthy gave two centralized deadlock detection algorithm called two-phase algorithm and one-phase algorithm. And it is going to fix the problems related to the centralized algorithm which may have. And these two algorithm is going to collect two consecutive status report, as well as, or it is going to keep the two status table at each site to ensure that the control site gets a consistent view of the system. So let us discuss about the two-phase algorithm. In two-phase algorithm, every site maintains a status table that contains the status of all the processes initiated at that particular site. The status of the process includes all the resources logged and all the resources being on the waited upon. It means the table which is being stored, it contains all the information that how many resources are already allocated and how many resources are still in the waiting position. And periodically, it is going to designate a site. Periodically, a designated site means the central coordinate. The designated site is going to request the status table from all the sites. Now, this kind of table is being maintained by all the sites. And the designated site is going to request the status table from all the sites. And depending upon that table, it is going to construct a wait for the graph based on the information which is being received in the form of a table. And then it tries to search for the cycle. If there is no cycle, then the system, it reveals that the system is free from the deadlock. Otherwise, that particular designated site which has asked the table from all the sites again is going to request the status table from all the sites, and then again constructs a wait for the graph using only those transactions which are common in both the reports. So it means it is asking two times. One time it has asked if there is no cycle, it's okay. But if it contains the cycle, it again asks all the sites to send the report. And then again, it is going to match the request status table from all the sites, and only those, which includes only those transactions which are common in both the reports. And if the same cycle is detected, then the system is declared to be the deadlock. So since it is doing the things two times, that is why it is called two-phase algorithm. Now, it is claimed that by selecting only the common transaction, which is found in the two consecutive reports, the algorithm gets the consistent view of the system, because it is one of the important aspects that whenever it is being asked, whenever a designated site is going to ask for the report, every time it should get the consistent report, means the updated report. So if a deadlock is going to exist, then the wait for condition must exist in both the reports. However, this particular claim is going to be proved as incorrect because uh, it may be possible that a cycle in a wait for the condition of the transaction common in both the consecutive reports does not imply that there is a deadlock. So in that particular case, this two-phase algorithm may report false deadlock. So by getting these two consecutive reports, the designated site reduces the possibility of getting an inconsistent view, but does not eliminate the possibility of false deadlock. So that is the drawback of this Ramamurthy two-phase algorithm. So they come with the idea of another algorithm, that is one-phase algorithm. This one-phase algorithm requires only one status report from each site, as it is being asked two status report from the two sites. Now, each site maintains its two status table, as told earlier also. First is the resource status table, and second one is the process status table. Now, the resource status table of a particular site keeps the track of the transaction that have been blocked or waiting for the resources is stored at that particular site. And the process status table at a site keeps the track of all the resources which are logged or in the waiting state for by all the transactions at that particular site. And periodically, the designated site is going to request both the tables from every site and constructing its own wait for the graph, depending upon those transactions for which the entry in the resource table is going to match and the corresponding entry in the process table. So whenever it is trying to frame the WFG, it is trying to look for both the kinds of table separately. One is process table and another is the resource table. So if there is any transaction which is represented by the process table, whether that entry is available in the resource table or not, corresponding entry is there or not. And then it is going to search the wait for the graph for a particular cycle. If no cycle is found, then the system is not deadlocked. And if cycle is found, then it means there is a deadlock. So this one phase algorithm, now the improved version of two phase algorithm has the capability to detect. It is not able to detect the false deadlock because it is going to eliminate the inconsistency in the state information by using only those information that is common in both the tables. So this is going to eliminate the inconsistency introduced by the unpredictable message delay. For example, if I take an example, if the resource table which is maintained at particular site S1 indicates that there is a resource R1 is waited upon by a process P2, that is P2 to R1. P2 has sent a request to the R1 and P2 has to wait because R1 is busy. R1 is allocated to somewhere else. And the process table of the site S2 indicates that the process P2 is waiting for the resources R1 by representing an edge that is from P2 to R1, which is constructed in the CFG of that particular site. If either of these entry is missing from the resource or the process table, then it is possible that the request message or the release message from the site S2 to the site S1 is in transit and P2 to R1 cannot be asserted. So in this way, we can conclude that one phase algorithm is a little bit faster and require the transaction of lesser amount of the messages as compared to the two phase algorithm. However, it may be possible that it require more storage space because every site has to maintain two status tables and exchanging bigger messages because the message contains two tables instead of one. So that is all about the one phase algorithm of given by Ho Ramamurthy in centralized algorithm.